this is the third part of Lesson 2, Part C. There are two main things you need to be able to do from this part of the lesson. So you see a function here. The one thing that you must be able to do is determine whether the function's inverse is also a function. We're going to use calculus to do that. You may have done it differently from another course. Perhaps you graphed it and saw that it passed the horizontal line test. But we're going to use calculus to show that the function's inverse is also a function. And then the second thing we're going to do is find this. I'm going to write it and see if you can determine what this is actually saying. That's one way to write it. Another way to write it is like this. So this is asking for the derivative of the function's inverse at 3. And we're going to talk about how to find that. And again, we're going to talk about how to find whether or not the function's inverse is actually a function to begin with. So here we go. We're going to determine whether or not this function's inverse is also a function. To do that, we're going to take the derivative. In this case, the derivative of this simple polynomial is 5x to the power 4 plus 1. Now, if you look at this derivative, if you look at this function, there's something special about it. And the thing that's special about it is this function is always greater than 0. The slope or the derivative is always greater than 0 for all x. The upside down a means for all x. Now, why is that important? Think about it. If the derivative is always positive, what is that telling us about the function itself? If the derivative is always positive, it's telling us that the function f is always increasing. Always increasing. It's always getting bigger for all x because the derivative is always positive. And therefore, this will pass the horizontal line test. The formal way to say that is f is 1 to 1. And that's my son in the background. F is 1 to 1. And when f is 1 to 1, we say, therefore, f has an inverse function. The inverse is a function. So that's what I'd like to see. Now, you could find that the derivative is always negative, then f is always decreasing. F is still 1 to 1 in that case, and then f has an inverse function. So now we're going to look at this formula. First thing, the way I'm going to show you this is I'm going to give you the formula, show you how to use the formula, and then at the end of the lesson, show why the formula works. Okay, so this is the derivative of the inverse function at a value b. And that's going to equal 1 over f prime, not at b, but at a. So let's say we have y equals f of x. Here we would say that f at a equals b. And we would say that the inverse at b equals a. So that's an important relationship of a and b. So at first glance, this formula seems not too bad. The derivative at b, the inverse, is 1 over the regular function's derivative at a. So we're going to go back to the other function, and we're going to see, I'm going to give it to you, and we're going to see if you can solve it without me saying anything. So pause the video and see if you can find the derivative. This is from negative infinity to infinity. And I would like you please to find the value of this. I'll say at 3. So the derivative of the inverse function at 3. And you're going to utilize the formula above here. So pause it and see if you can figure it out. Okay, so you should be back now. And the goal to this, the key to this, I'm going to make a note here, the key. A lot of people think this is b, and then they plug b in for this. I do not want to simply find the derivative of the function and then plug in 3. You see, b and a are different. So the key is to find A. That's the key of the problem. We have to find what the corresponding value is, and that's not really calculus, that's more algebra. All right, so how do we do that? Well, I know from this that f inverse of 3 equals A, so I'll scratch that out. Underneath it, I can say that f inverse goes through the point 3, comma A. That means the function f itself will go through the point a, comma 3. So if we look at our function above, f of x equals x to the fifth plus x plus 1, then 3 is the outcome, and a is the input. And we have to determine the value of a. So make it more clear here. So we have to find, again, the value of a. Now, to find this, there is only going to be one value of a. We already showed that it's 1 to 1, meaning the function's always getting bigger. So if there's a value that works, there can only be one value that works. Now, in a previous course, perhaps you use synthetic division here after finding one root. But your initial route, whether using synthetic or not, is to find, through plug and chug, find one that works. A little bit of guess and check. So we can plug in 1, and 1 plus 1 plus 1, in fact, equals 3. So we know A has to equal 1. So again, F inverse went through 3, comma A. F of x is going to go through A, comma 3, and we found A to be 1. So F contains the point 1, comma 3. And back to our formula now. So the derivative of the inverse at 3 equals 1 over f prime at 1. The key was to find the 1. So f prime of x, we found this earlier to be 5x to the fourth plus 1. F prime of 1 equals 5 times 1 to the fourth plus 1, which equals 6. So the answer is 1 over 6. The derivative of the inverse at 3 equals 1 over 6. I'm going to end this particular video at this point. In the last video, we will see a couple more examples of this exact utilization of the formula. We will derive why the formula works, and then that will conclude lesson 2. The end.